So hi, everyone. Welcome to another stat seminar. Today we have Chris Harshaw giving a presentation. So first, for a little introduction. So Chris is a FODC postdoctoral fellow hosted jointly between MIT and UC Berkeley. He obtained his PhD in computer science from Yale University, where he was advised by Daniel Spielman and Amin Karbasi. His research addresses theoretical aspects of causal inference and data science, particularly algorithmic and statistical problems arising in the design and analysis of randomized experiments.
Thank you. And thank you, Emma, for that wonderful intro there. My name is Chris Harshaw. This is joint work with Jessica Dye and Paula Gradu, who are grad students at UC Berkeley. Okay, so before we begin, a few things. The first is that I always like to tell an audience before I talk that I'm a person who stutters. I feel more comfortable saying that, and I hope you get more comfortable hearing it. The second thing is I will skip over all of the proofs here. Third, I'm on the faculty job market, but a shameless self-promotion. And third, please ask me clarifying questions throughout. So I built enough time in the talk to have lots of back and forth. So please ask me questions at any point. Okay, so a bit about what my research is. I design algorithms, methods, and theory for causal inference with a focus on randomized experiments. And randomized experiments are one of the most ubiquitous causal inference methods, and they're used in a variety of disciplines, from clinical medicine, public policy, economics, corporate A/B testing, and even human-computer interaction. And the empirical evidence that's gathered in these disciplines through randomized experiments informs some very consequential decisions that we make, like which medicines get prescribed, which social programs get implemented, and which corporate strategies that we follow. And what's very exciting is that recent technological advancements in, say, measuring certain data or performing certain interventions offer really exciting opportunities for new types of experimental investigations. So for example, the researcher may have access to high-dimensional covariates, like in genomics data, and they may want to use these to improve the design of their experiment. The researcher can collect complex network data, which describes how certain experimental subjects will interact. And in fields like public policy and health, this can even define new causal questions to investigate. For example, if I run some anti-bullying campaign, is there a positive spillover effect? That is, are the students who are not directly targeted by the campaign, are their amounts of bullying reduced? And finally, with the proliferation of lots of mobile health devices in our mobile phones, we can run real-time and interactive interventions. And we might seek to increase statistical precision by running experiments in an adaptive way. And that's what this talk is going to be about. Now, even with all these really cool technological advancements, the downside is that conventional statistical approaches can't handle or weren't built to handle complexities like this in randomized experiments. So for example, if we were trying to use high-dimensional covariates like those found in genomic data to improve the design of our experiment, we have to ask about balancing high-dimensional vectors between two groups, which can be a challenge. So if I was to independently assign treatment and control, then there must be some imbalance between some covariates, given how high-dimensional they are. And even matching approaches won't work simply because there's no good matches in high dimensions. Designing experiments when subjects are interacting is also a challenging question. If you were to independently assign treatment and control, then it will happen that most of the subjects in your experiment have about half of their neighbors treated and half control, which doesn't allow for lots of variation to investigate certain types of spillover effects. And finally, understanding the extent to which adaptive experiments can improve statistical precision is also a challenging problem. For one, that the space of adaptive designs is so much broader than those non-adaptive ones. And a key theme in my research is that these statistical problems I often find are inherently computational, and therefore we need to design algorithms to address them. And what's more exciting is that these computational questions that arise are often novel, and so we have to innovate in the algorithms that we use. Okay, so let me switch gears a bit now and talk about adaptive sequential experiments. I'm going to work with a simple running example here. So I like going to the gym, and at the gym, something I often wonder is, do words of encouragement from a coach affect the performance of a beginner athlete? And so to test this, here's the experiment that I would run. I would collect my beginner athletes here, and I would hire a professional coach. Okay, he's going to be a lot of money here. Now I'm going to run the following experiment. I'm going to either have the coach give praise or just some facts about the movement that's going to be run. These are the treatment and the control. And what I'm going to measure is their time on the 100-meter sprint. Okay, so the first person comes into the experiment, and the coach will flip a coin, and he'll either say some praise, so that's the treatment, like, I believe in you and you can do it, or he'll give the control, which is just some fact, like a standard time for a 100-meter sprint is 35 seconds. Okay, so not too inspiring, but that's the control, so that's fine. Okay, and then he'll pull out his timer, and the participant will do their best to sprint 100 meters, and we're going to record what the time is. And then the next person will come in here. Again, they'll get either treatment or the control, which will be randomly assigned to them. We'll pull out the clock, we'll have them run, sprint 100 meters, and record how long it takes. And we'll keep doing this until everyone goes through the experiment, and the coach has collected all this experimental data here, who got assigned to which treatment and how long it took them to run. And from this data, the coach will then estimate the effect of what encouragement is. Maybe it shaves off 5 seconds in the sprint time for a beginning athlete here. Now, in a standard experiment, the treatment probabilities are, they're not randomly, they're normally, in a normal way, selected before the experiment starts. So we fix some bias of the coin P, and for everyone that comes in, we'll assign treatment with probability P and control with probability 1 minus P. And that's just the way it is. But in an adaptive experiment, the treatment probabilities are adaptively selected using prior observed outcomes. So for example, we can see what the outcomes were of people who previously ran and use that to guide what our new probability of assignment is going to be. And what we're asking in this work is how, or to what extent, can adaptive experiments improve statistical precision for estimating the causal effect? So before I go into any more details here, are there any questions about the setup that we have here? Awesome. Oh, yes. Yeah.
Does it make a difference whether we're allowed to see the previous, so suppose we're allowed to see only the previous assignment results, but not the outcomes? Or using we have access both to everything that's happened prior to 10T? Everything
that's happened. Yeah. So if you didn't see the outcomes, if you just saw the assignment, you can do all that before you see anyone. Like I could pick a probability P, flip coins, make my assignment in advance. So seeing those assignments, you can correlate them any way you want. Here, we're not going to correlate them at all. They'll all be independent with probability P. But what's going on in the adaptive experiment is that we see the outcomes and the assignments, and we'll use those outcomes to improve the precision of our estimator. Great. Any other questions here? Yes.
Well, why there will be some challenging if you just use an identical data to decide the issue. So what kinds of issues there will be?
Yeah. So maybe I said too much in my first slide. The first slide was more of like a what do I generally work on? So there won't be anything high dimensional going on here. In fact, I'm going to assume there's no covariates at all. So I don't even look at stuff like how tall is the person, how long is their legs. I'm not going to look at any covariates here. So it's just a simple no covariate setting here. But I have other work that deals with high dimensional covariates, and I'm happy to talk about that another time. Yeah. Great. Okay. So let me give a historical detour here on adaptive experiments. So the earliest work that I know of that addresses the problem we'll be talking about today comes from 1952 by Herbert Robbins. It's a really cool, really prophetic paper. And I'm not going to read all of it to you here, and I wouldn't try reading it up here, but let me just point to the parts that are highlighted in blue. So first, Robbins says, okay, well, what if, what's the optimal allocation that would minimize the variance of some estimator that I have? Now, the allocation rule will depend on outcomes that I haven't seen yet, so that's a challenge. And then he goes on to describe this two-stage design, which is actually something that's analyzed by recent works here. And I'll get to them in a little bit, but the idea is in one stage, collect data with probability half, and then use that data to estimate the optimal probability, run that for the final stage there. Okay? And then he ends this paragraph with saying, suppose we had a fully adaptive experiment, one like the kind that I just talked about, where you at each point can look at the previous points to decide the probability. And he lists this as one of the very cool open problems at the time. And there's like 6 open problems in this paper, and it's really cool to see how they've determined work on sequential analysis. Yes. Okay, there's many other types of objectives that you could look at. So even earlier, Wald was concerned with optimal hypothesis testing in a sequential regime, which is something different than trying to make the variance small, but obviously related. And throughout the 70s and on, there was many different, an explosion of different kinds of adaptive experiments that could do different types of things. Maybe you want to make the total treatments that you use small, or maybe you want to say, hey, I want to have some power against the null, and conditioned on having that power, or rather subject to having that power, I want to do as little harm to the subjects as I can. And you also might want to identify subgroups that are relevant for the certain treatments that you're working on, groups where you have a high treatment effect. Okay, but then who critiques most of these response adaptive designs, particularly those developed in the 70s to 90s, as being myopic and having adverse effects on power, and they're evaluated primarily through numerical simulation rather than through like a well-developed theory. Okay, so one question is, can adaptivity be harmful? Can it actually lead us astray? And some people think the answer is yes. So in around 2011, the FDA releases this statement, which essentially says, use adaptive designs sparingly or cautiously because we don't know how well they interact with certain inferential procedures. And as early as last year, or as recent as last year, and Raffi even have this paper that says small pilots, namely those two-stage types of designs, can be misinformative and can have the adverse effect of increasing the variance. And we're going to see something like this in this talk here. And so all this to say that I think there's a need for more principled types of adaptive designs, and we'll be taking a first step in that direction in this paper here. Okay, so let me go ahead and define the problem that we'll be working on, which is adaptive Neyman allocation. So I'm going to be working in the potential outcomes framework here, and let me describe what I'm doing in the non-adaptive setting first. So for example, there's T experimental units here. They're going to be maybe the participants in our clinical trial, or those people that I paid to come to the CHIM, and they're denoted by integers small t, which take value from 1 to big T. Maybe there's people running the experiment up there. That's what's going on. Okay, so there's capital T treatments here. They're denoted Z1 to ZT. They're binary, so you got the treatment or you got the control, and they're assigned independently, each with probability P. So this is what Arnold was doing in the intro slide. And each unit has 2 potential outcomes. So there's the outcome that you would observe, YT1, if you were given the treatment, and the outcome you could observe, YT0, if you were given the control. And so this is like, how long does it take you to run a 30, or rather a 100-meter sprint if I said very nice, encouraging things, or if I just gave you like facts. And in this talk, the potential outcomes that I'm working with are deterministic. So they're not random, they're not IID, they're deterministic things. And the only source of randomness is in the treatment assignment itself. So that will serve randomization as the basis for all of my inference here. And that's referred to as this design-based inference. Okay, so the outcomes that I observed, those are capital YT. They're just in math, what I had said beforehand. If you get assigned the treatment, we'll observe YT1. If you get assigned the control, you'll observe YT0. And the observed outcome is a random quantity because treatment assignment itself is random. But again, the potential outcomes are deterministic here. And what we seek to estimate is the average treatment effect, which is simply the average over all the units in my experiment of the contrast between their outcome under treatment and their outcome under control. So what's the difference in the time that it took you to run that 100-meter sprint? And to estimate the average treatment effect, we're going to use the Horvitz-Thompson estimator here, also called the inverse propensity-weighted estimator here, which is simply the average of the outcomes weighted by the following quantity here. If you were assigned treatment, weight by 1 over the probability of treatment. If you were assigned control, weight by negative 1 over the probability of control. And so in our example here, this will be P and 1 minus P. And this estimator is unbiased so long as the probability is within 0, 1. And a way to see that is to take expectation from here, move it inside, and you'll see that this guy will be 0 if ZT is equal to 0, and he'll be 1 over probability of ZT being 1. If ZT was equal to 1, the probabilities will cancel out, and we'll get back the average treatment effect. So it's a very standard estimator to use in this setting here. And before I go on, let me continue. Let me define some few moment analogs here. Okay, so these this S1 will be just the average over all of the units of their outcome under treatment squared, and I'll divide by the square root. And the same thing for S0, just under control. And the way I think about this is design-based analogs for the second moment here. That's what I'm defining here. And I'll also define an uncentered correlation row, which is also called the cosine similarity here. That's just the average of the product of the outcomes divided by their second moments. And this, by Cauchy-Schwarz, just takes values in -1, 1. So I'm going to talk about the variance in terms of these quantities here. So before I go on, are there any questions about what these quantities are? Yes.
So just formally,
Mhm.
I think this is just like, I just want to make sure like how hard you're committing to design-based inference.
Mhm.
Right. So like you're thinking like the T units are the entire population.
That's exactly right.
And you're not interested in generalization to a larger population. And so this is like the true moment of the distribution. This isn't like an empirical moment.
That's exactly right. Yeah.
And
Yes.
this would only be observable like if you happen to assign everyone to 1, or you happen to assign everyone to 0.
Yes. So we haven't talked about it yet. We'll talk about it later on. But I can estimate these quantities. But yes, as such, yeah.
These are population.
These are the all the YT1s and all the YT0s. That is the population that we're looking at. And happy to talk about like why might one want to do design-based versus zero population-based, and what are the pros and cons of each. But unless anyone wants to hear about that now, let me just like save it for a later time. Great, thanks for that question. You want to come in? Okay, no? Okay. Is it Parents' Weekend? Is it Parents' Weekend? Okay. I was in a, it doesn't matter. It's a long story. I thought it was Parents' Weekend. Okay, but what's more important than Parents' Weekend is how to reduce the variance here. So let me write down what the variance is. So the normalized variance is equal to the square of the second moment times 1 over the probability minus 1, and a similar type of quantity for the treatment here. Okay, so let's break down what's going on here. These first two terms depend on the second moments and also the probability the experimenter chooses here. So we can try to make the variance small by optimizing P in these first two terms here. That third term, nothing we can do about that term. We just suffer the cost of whatever it is. Okay, but I'm now writing the variance in this normalized way to highlight that the rate of the variance is 1 over t, and it's this constant that I'm going to be optimizing here. That's this part here. So that's where the efficiency gains will be, not in the rate, but in that constant. And before I move on, let me just say, if this S1 was very, very large relative to this S0 here, I'd want to make this term small to counteract that. So I'd want to have a high probability of assigning here. So the idea is like, if this group is very spread out relative to this one here, to make the variance small of the Horvitz-Thompson estimator, I should sample more from this group here. So that's the kind of intuition what we're going to try to be doing here. So the Neyman design is simply to use the optimal probability, which if you work the calculus out, it's just the inverse of 1 plus the ratio of the second moments here. Okay, and then the variance you would get out is the Neyman variance, which takes the following form. It's just 2 plus 2 times 1 plus the correlation times the product of the second moments. So what I've done, really, the efficiency gain is going from the sum of the squares of these second moments down to their product. So it's kind of like an arithmetic to a geometric thing. That's what we're like gaining if we were to use the optimal Neyman design. But the problem with the optimal Neyman design is that it's infeasible. It depends on all the outcomes. And if I don't know those outcomes in advance, then I can't run this design. If I did know the outcomes in advance, I could run this P, but I wouldn't have to even run the experiment. So I would say the Neyman variance serves as a benchmark for us to achieve, but we can't actually hope to exactly run this design. So the question is, can we provably obtain the Neyman variance in an adaptive experiment? That's what we'll be trying to focus on here. Okay, so let me go over about these 2 prior work papers here. There's many papers on different types of adaptive design problems, but the following 2 are related to our definition of adaptive Neyman allocation. As I mentioned, they both use this kind of 2-phase experimental design, where you sample for one phase, try to estimate the optimal P, and play the optimal P, estimate optimal P for the second phase. Okay, so Han et al. In 2011, they make an IID superpopulation assumption. They're sampling units from a distribution, and they're motivated by semi-parametric theory, but what comes out is the same kind of objective as we're looking at here. And they can show they can get within a constant factor of the Neyman variance in large samples, but they're not going to achieve the Neyman variance. To be fair, their paper is focused more on the validity of certain inferential procedures, not on attaining this Neyman variance per se. Now, Blackwell et al. Last year take a design-based approach, again, putting forth this 2-phase design, but there's no theoretical analysis of what the variance is. It's more of running simulations and arguing about good results that practitioners should use. And so the main contribution in this paper is that we're going to construct an experimental design whose variance will provably converge to the Neyman variance, and we'll develop inferential methods that will take advantage of this as well. So that's the main contribution here. Are there any questions about what that contribution is, or kind of what the Neyman variance is, or what it means to be getting close to it? Yes. Huh? That's a great question. I say that for almost the last slide. We're not going to assume anything about the order in which units arrive. So we will have some conditions that will say outcomes can't be growing too large. They can't be all 0. We'll have some kind of assumptions like that, but we'll place no assumptions on the order the outcomes will come in. Yeah, so like this is an adversarial ordering, but from an online point of view, the ordering is chosen before the experiment is like the sequence is chosen separately from the experiment. So the adversary is not like seeing stuff. Yeah, the adversary is just choosing the sequence beforehand. Great. Okay, so let me get into what our work is. So our experimental design is called Clip-OGD. I'll explain where that name comes from in a little bit. But let me go ahead and get into the adaptive setting here and what estimation looks like in the adaptive setting here. So again, we're looking at the average treatment effect. And the adaptive protocol is that for each unit, I will assign treatment with probability PT and control with probability 1 minus PT here. And I'll observe that outcome, Y of T. But the catch now is that the probabilities can be random. These are just conditional probabilities here. They can depend on the data that I've observed in the past. Okay, and so we're going to use the adaptive Horvitz-Thompson estimator, which rather than using the marginal probabilities of assignment, because we don't know those in an adaptive experiment, since they depend on the outcomes in funny ways, we're going to use just the conditional probabilities of assignment here. Same exact estimator, just using the conditional probability you saw at this time. Okay, and this is also unbiased.
Can I ask you a question, Chris? Because I'm getting lost now. Yeah. So you said that you didn't have covariates on the individuals participating in the trial. So what is PT? I mean, is PT the same for every T, but it's going to be based on past data? Because otherwise, how does it depend on the particular T person?
Yeah, that's a good question. So in this talk, there's no covariates. If you call me in three months, I can let you know what happens with the covariates. But the way PT is working here, is like the idea is that you would like to know which group has a larger second moment. And so you would like to play Ps that lets you learn what those second moments are, and then move to the group that has a larger second moment.
Right.
That's the idea of what's going on.
What I don't understand is at time T comes person T, okay?
Yes.
And were you already able to see the outcome of earlier individuals to allow you to use that? I mean, yeah, is that clear, my question? I mean, what is PT based on? What kind of data are you going to use to calculate PT?
Right, you'll look at ZS and YS. For all S, they're less than T.
Okay, so you will have already seen the outcome, because usually in many trials, you have to wait to see the outcome. It doesn't come instantaneously.
That's exactly right. So if you have to wait until the trial's done, you cannot rerunning an adaptive experiment.
Okay.
So we're only focused on the settings where you can be running an adaptive experiment.
All right. Okay.
Now, so everything I'm saying is like fully adaptive. Like at time T, I can use everything in the past, even T minus 1. You can relax some of this. I believe I haven't worked it out, so don't quote me on this. But if you're able to batch things, and you have a large enough batch, like you have a large number of batches growing with capital T, then this kind of stuff works out as well. But just some of the rates are a little bit worse. Okay. So yeah, you're completely right that not every experiment can be run in this way, but I'm focusing on those that can be run in this way.
All right, I got it. Thank you.
Awesome, great, thanks. Okay, so let's see here. So we're going to use the adaptive Horvitz-Thompson estimator here, and now let's calculate what the variance is. The variance of the normalized Horvitz-Thompson estimator will have a similar form as but beforehand. There are two main terms. So this first sum here is over all of the units, and it has the outcome under treatment squared times the expected 1 over the probability. The probability is random, so this is a random thing. That's why the expectation shows up here. And then we have YT0 times the expectation of 1 over 1 minus the probability. And so this term, we can hope to make small by selecting these probabilities in an adaptive way. But this second term, or the 1 over there, nothing we can do about that. That we just have to take wherever we can get there. Now, what's the kind of idea to making these terms small? Again, if YT1 was much, much larger in magnitude than YT0, I want PT to be much larger, closer to 1. But the challenge there is that how small can we make this first term if we only adaptively and partially see outcomes? So I have to commit to a probability PT before I see the outcome. And when I see the outcome, I only see one of them. So given that this is the setting that we're in, how small can we make the variance here? That's the real question here. So the first key insight of our paper is that the Neyman design, the one that we're thinking about, is the best fixed design when that random probability is chosen to be little p for every single unit here. And if you just chose that, what would that be? So that's the best Neyman design, best fixed design. And comparing to the best fixed design is a regret minimization problem. So that's the key insight. So let me go on a little bit more about that. And before I do, remember this term here. This is the term that we can control. So yes, please, yeah.
Previous slide, you're taking the expectation, right? Is that the expectation with respect to a particular policy that will lead you to choose the PT?
Yeah, so basically you have some policy that you've chosen beforehand. Strictly speaking, the policy is a deterministic thing. It just says, what have you observed, and map it to a probability. And when you observe random things, that means that this whole process of assignment is random. So the probabilities are random, and that's what this expectation is with respect to here.
Okay.
Just the treatment assignment.
For example, right, like I reorder, right, like I'm the adversary, so offline gets to reorder the T units. I'll actually change that expectation.
You will change the expectation. Yes. Yes.
Okay.
That's exactly right.
Okay, so there's really like a whole family of potential expectations that are somewhat dependent on the ordering.
I'm going to fix.
Doing this for a fixed order.
Yeah, I'm working with a fixed ordering here.
Okay.
There's only one.
Unknown but fixed ordering.
Unknown but
Okay.
fixed. Yeah.
Okay.
So there's one ordering here.
Okay, so that's not a source of randomness you have to worry about.
No. In fact, you could this problem would become easier in some sense if the order was random.
Then you can integrate that. Yeah.
Yeah, but we're not going to allow for that. We're going to make it a little bit harder. Okay, and that kind of makes sense in some situations where you believe there's like non-stationarity or drift in your outcomes. Like maybe the first people who came up were those who really wanted to see Arnold, or sorry, those who first came didn't care they saw Arnold or not. Yeah. They were so excited. They told all their friends came. Yeah. That doesn't depend on anything random. They just saw Arnold. Yeah. But so if we use a design that assumed they were all in some random order, then that would be not appropriate.
And to make it totally clear, so if I told you all of the Ys, both potential outcomes, but not their order, and your policy, you still couldn't compute the expectation.
That is correct.
You have to know the sequence and all the potential outcomes in order to actually evaluate that expectation.
Yes.
Okay.
Yes. Awesome. Great. Thank you so much for clarifying this. You're doing a lot of my work for me here. Any other questions here? Okay. Awesome. So let me define a new metric. It's a certain type of regret that we're calling Neyman regret here. So for each t, let's define this cost function ft, which maps a probability into the reals, some kind of cost, as follows here. So for ft, that cost will be yt1, the outcome under treatment squared divided by p, plus the outcome under control squared divided by 1 minus p. Now this is, I should have had it all on the same slide, but this is kind of capturing what unit t can contribute to the variance, or rather the part that we can control here. So this term without the expectations here, that's exactly what this cost is. So that's where the cost is coming from. And the Neyman regret of an adaptive experimental design is equal to this following quantity here. This is the cost of the design that you play contrasted with the best design in hindsight, the one that knows all of the outcomes beforehand. Now this regret is a random variable here because what you play is random. But the Neyman regret relates to the variance in the following way. If you look at the difference between the true variance of your design and the Neyman variance, if you look at the difference of these two things, it's equal to 1 over t times the expected Neyman regret. That's what the definition of these things works out to be. That's why I was chosen. And what this says is that convergence to the Neyman variance, that is to make sure that additive error becomes very, very small, is equivalent to ensuring that the Neyman regret is sublinear in T here. So I would say that this kind of informs us that this adaptive Neyman allocation problem is inherently computational, in the sense that to achieve this like statistical guarantee, which you'd like to do here, you have to solve some type of online optimization problem, which typically requires sort of like sophisticated algorithmic methods. All right. Are there any questions about this relationship between, yes?
So what's N here?
Oh, goodness. N is T. I thought I removed all the N's. Sorry. Okay. You've
Okay.
caught some N's. This should be a T. This should be a
It's
T.
times B sub T.
T sub, yeah.
The same T.
Oh, no, these are N. No, sorry. I'm right. Sorry.
Okay.
N is for Neyman. Sorry. This talk used to have some other N's in it, and I was told that was a bad call.
Okay.
Sorry. N means Neyman here. This is the optimal Neyman variance. Maybe V star is a different type of
Okay.
way you could look at.
So
So
what notion are we converging, right? Like what's growing in order for us to converge?
that's a great question.
Is T growing, or is like our algorithmic complexity growing, or?
I've been a little bit informal about this. So everything I've said so far has no like notion of like asymptotic sequence here. Nothing can be growing. So all I've said, like what I can still hope this regret is sublinear in the sense that it's bounded by like something that's less than T, and maybe there's some constants depending on outcomes maybe or something. So that's you can, this is all a finite sample thing that you could do. You can make this small any way you want. But it's very natural in design-based inference, and I wasn't going to formally define it too much, to consider like a sequence of experiments. And within the sequence of experiments, saying, oh, well, the second moment is bounded away by from 0 by a constant, or the fourth moment's bounded. So there's a way that people work with asymptotics. We will not use any asymptotics until we do inference.
Okay.
So that's a good point. When I say converge, I'm being a little bit loosey-goosey here. The paper's more like clear about what this means. But if you don't like it for the name and stuff, just like all of it's finite sample anyways, so it doesn't really matter too much. Yes. That's a great question. So the question I'm just going to say it once more for people who are on Zoom is, why are you comparing to the best fixed design versus the best adaptive one? So two reasons here. Like one reason is because that's the problem that we started with. Like the problem that we started with was, okay, there's this optimal design, this non-adaptive one, which was infeasible to run in a non-adaptive setting here. With an adaptive setting, can we get close? So like you could still ask, well, why that benchmark? Like why? So it's cool. That's the problem. People have like, one answer is socially, people have, worked on that. And so we're doing what we've worked on. On the other hand, the optimal adaptive design is way, way too good. So like if you mean the adaptive design where you know what all the outcomes are, then what I could do is don't look at that. What I could do is I could just choose at each time whatever minimizes this. And that'd be like looking ahead in the future. So that's way too good. So we cannot hope to like compare to that. So it's not so much like mathematical or like scientific answer. Maybe at the end, I'll talk about min-max regret, which will be a type of answer for what you're asking about. Like this benchmark can't be improved upon. So that's one reason. I haven't proven that yet. So this is what I'm working on. Yes. Oh, you're right. So you're skipping ahead a little bit here to see how well we can do. All I mean to say is that if this was little o of t, this would be little o of 1. And so the normalized variance would like converge in that sense. As long as this is little o of t, you're fine. If this can be square root t, hey, that's great. That's definitely little o of t. So I haven't told us how good we can do, just that anything sublinear would be good enough to make this statement go through. Does that make sense? Okay, nice. Okay, so Okay, so these functions are convex. So this is an online convex optimization problem here. To convince you that they're convex, I'll plot two of them. Okay, so pros and cons. These are all convex, so we can use tools from online convex optimization. Great, but let's be a little bit careful here. The first is this is different from cumulative regret, like always doing the best action in terms of utility in hindsight, because we're trying to estimate the means, not play the best arm. Two different things. And in that setting, when you do stuff like that, the functions are linear here. Now, a technical issue is that these functions have unbounded derivative near the boundary. And so that means that standard algorithms, like standard OCO algorithms, won't be working here. And I'll show you why that's an issue. So we have to have new algorithmic techniques. So you may ask first, well, what about doing an online gradient descent? So gradient descent online works in the following way. I'm working in the full information case just to kind of show how this works. At the first iteration, you pick some probability P, let's say it's 1/2, and you have this cost function here. And you incur the cost of playing 1/2. Then you look at the gradient at where you just played, and you walk a little step in the negative direction here, okay? And this is what you play at the second round. And now that you've played this, there's this new cost that comes. You've now incurred the cost of your action. You can look at the gradient and walk a little bit in the negative direction here. And now you play this in the third round, and so on and so forth. So this is how online gradient descent works. And as you had mentioned, it typically gets square root t regret, but under some assumptions. Okay, and those aren't satisfied here, namely that the gradient is bounded. So let me show you what goes wrong. The gradient is not bounded here. So what goes wrong? First issue, mild one, gradient access. So there's this function here that depends on the outcomes. And so its gradient depends on the outcomes. So we can't know the whole gradient because only one of these outcomes is going to be revealed, but we can do stochastic gradient estimates here. So that's not too big of a problem. That's like totally fine. The real problem is this unbounded cost. Okay, so what happens here, the issue is that if you are well in the interior here, your cost is small. It's like a constant size. But if you accidentally got way too close to the boundary, then your cost will blow up. It'll be super large. Even getting too close to the boundary once will prevent you from having sublinear Neyman regret. So we have to make sure this doesn't happen. But what's the tension? The tension is that the optimal P could be close to the boundary. For all we know, we don't know that's not true. So how do we work around this? Okay. The solution we propose is probability clipping here. So the way that works is we're going to have some clipping interval at some time t, and whatever gradient descent tells you to do, I want you to project back into the interval here. That's the only like moving animation that I had. So that was a cool. This you're going to project back in. All right, and but what's the problem here? This clipping interval is small. I told you we need to get close to the boundary in order to know that we can get close to the optimal P star. So at each iteration, we're going to grow and grow this clipping interval here. And how we grow it is developed in like a technical way to make the proofs work as optimally as you can. Okay, so we call this Clip-OGD, clip for probability clipping, OGD for online gradient descent here. Okay, so this is the algorithm. I just want to point out a few parts. There's two inputs. What's your step size and how fast does this interval grow? Okay, so we're going to clip in this range, delta t to 1 minus delta t. Delta t starts as 1/2 and it gets smaller over time according to this rate alpha. And we'll talk about how to choose that in a little bit here. And of course, we're going to estimate gradients through stochastic gradient estimation using the Horvitz-Thompson principle here. Okay, and so here's the main result. But first, let me get through what the assumptions are. So there exists constant little c and big C such that this second moment is bounded away from 0. And this fourth moment here is bounded above by some constant here. So this prevents the outcomes from all becoming like 0. And this prevents the outcomes from growing too large. Any individual outcome can be 0, or any individual outcome can be large-ish, but they can't all be large or all be 0.
Sorry, the C's are themselves 0 and.
Yeah, so this thing is bounded away from, I should have mentioned, this is less than little c, or this little c is less than 1. It's going to come in helpful here. And this big C is just like a constant.
Okay.
And what this really means is that when I write big O, anything depending on these, I'm just going to like not tell you about. Okay, now the cosine similarity, we're also going to say, is bounded below, bounded away from -1. So it's between -1 and 1, but we're not letting it get exactly -1. The reason why is that these two assumptions together are needed so that the variance, like the optimal variance, is not exactly equal to 0. If this didn't hold, the optimal variance could exactly be 0, and the problem would not be an interesting one. It's kind of like an edge case. I should also add that under an IID assumption, these things should come to you essentially for free. So it's really like design based that we're having to make these assumptions. This is a really important one. This you'll definitely need, and it's not given to you if you were doing IID. And in particular, as Kevin asked, there's only moment conditions here. There's no assumption on the order in which these units arrive, so we can allow for any kind of non-stationarity and so on. And so the main result is that if we set the step size 1 over square root t, and we choose this alpha to be square root 5 log t here, then Clip-OGD guarantees that the expected regret is less than square root t, or sorry, it's order square root t. And when I say O tilde, I'm hiding some sub-polynomial factors here, which it's an interesting question where they can be shaved off, where they're inherent to the problem. I'm an optimist, so I think they can be shaved off. And I'd mentioned that this is the first experimental design which can provably obtain the Neyman variance in large samples here. All right, is there any question about this result here, what it means, how we chose these things? Yes.
Probably the way it's floating, but a common problem.
Mm-hmm.
I know a lot of people like to get away from that, but maybe estimating the weights directly. So with such an approach, work here, would it maybe relax the assumptions? Like, I imagine maybe you get away with like a variance on the weights themselves in the optimization. Because it's the 1 over the if you optimize 1 over the probability that you really.
So you're asking, can you? You're asking, can you place assumptions on the probabilities output by the algorithm?
And maybe, does it make sense to maybe assign, like, the probabilities imply, let's say, your rule for assigning treatment? Could you maybe estimate the inverse of that instead for the weights? Like, what weight do you give on different people? Like, that's what appears in your estimate. And that's.
So we do get to choose the probabilities here.
Yeah.
So we don't have to we don't have to estimate them, because they're known to us.
Optimization problem.
Mm-hmm.
Would it, or maybe it's not at all possible. Is there any way to maybe reframe it as estimating kind of the inverse propensity weights rather than the propensity themselves?
You don't have covariance though, right? So just not.
There's no covariance here. Yeah. So we're working in an experimental setting here where we choose the probabilities. So I think the right framing is like, if there was to be changes here, you would change how you choose those probabilities here. You can also not choose the Horvitz-Thompson estimate. You can choose other ones and try to do the same game of how to make its variance small. Can it still be cast in this kind of like separable online optimization problem? We've also been exploring that, as I kind of mentioned on Freya. Any other questions here? Yes, Kevin. Oh, what a great question. You're not going to love the answer. That's why. So this is the very CS thing to do. Is I just don't say. So my worst case bound, which you're not going to love. No one's asked this yet. I was hoping you asked what subpolynomial factors show up, but you asked the question I don't want to answer. Right now, it can be exponential in big C divided by little c. So that means that if the second moments and fourth moments are kind of like close-ish, then okay, we're a constant. But it's exponential in the difference of in the ratio of these two things. So if this is a constant and this is a constant, guess what? It's still a constant. But yeah. So, and I think that's not like fundamental to the problem. I think that's through the technique that I use to analyze this. I'm happy to tell you more about that. So I think the subpolynomial factors here and the ugly dependence on constants, that can be fixed. So we're running low on time. Yes,
Algorithm doesn't need to know this.
that's exactly right. And I should mention that if you happen to know little c and big C, you can use those to further optimize what these choices are, and then you can get something that is still square root t, but like is a little bit better in terms of the constants, but like not by an extraordinary amount. Yeah, cool. So let me kind of run through some of the other things. We developed asymptotically valid inference here. So now I really am relying on asymptotics. None of that stuff was literally asymptotic. This is really like there's a sequence, so on and so forth. We estimate the variance in this kind of way. And this says this is a conservative estimator for the variance in large sample sizes. Conservativeness you have to do in design-based inference. That's just the way it is. And if we use a Chebyshev bound, this will cover at the nominal rates. We're very close to proving essential limit theorem. Not quite there yet. But if we were, this would go through with essential limit theorem. Okay, how do we estimate this variance here? Well, okay, you can't run bootstrap because this isn't like IID. So I can't rerun the experiment here. So that's a problem. So one idea is let's write the variance down and we'll just estimate it, just like we estimate the average treatment effect. Inverse propensity weight, stuff like that. That should be totally fine. Well, the difficulty is that we don't know what these expected values are because I only see one run of the experiment. I don't get to see multiple runs. So I don't know what these values are. So it's tough to estimate what this like quadratic form is. So can we even estimate the finite sample variance is a good question. And one trick is that we can say, oh, well, the finite sample variance quickly approaches the Neyman variance. So how about I estimate that instead? So just in symbols, we approach the Neyman variance. This is a very simple closed form. What to do here? The second moments are estimable quantities here. Unfortunately, the correlation is not. This is common in design-based inference because it depends on yt0 times yt1. Never can observe that. So we have to upper bound. And this is very common. Again, this is a very standard thing. Once you have something you want to estimate, it has an inestimable quantity, you use an upper bound. So we estimate this. So our estimator is just simply kind of like looking at this and kind of constructing a conditional Horvitz-Thompson estimator here. Nice. Okay, there's some additional results in the paper, namely two-stage designs can't work well in design-based inference here. And second, what I think is very cool is that if some allocation method has sublinear cumulative regret. So let's say you said, oh, I'm trying to assign the best arm, or the arm, I'm trying to assign ways that's competitive with the best arm in hindsight. If you do that, then you must suffer superlinear Neyman regret. In fact, the order of your variance even blows up. So this shows that cumulative regret and Neyman regret are incompatible things. So estimating the effect of the best arm, or estimating the effect of the arms, and trying to play the best arms are like different types of objectives that you can try to trade off. Okay, we have some simulation results. We don't really have time to talk about this too much. What I want to mention briefly is Clip-OGD. So here's the Neyman design. It's optimal but infeasible. Here's Bernoulli. Here's the two-stage. Clip-OGD does converge, which is nice. Two-stage does not converge, which is to be expected. But there is this adaptivity overhead here. You can mitigate this by choosing the step size a little more carefully. So this can actually start as low as Bernoulli, but I only know that from like trying different step sizes, which is not really fair to report. So I'm not showing you what that is. It's in the appendix of the paper. And in fact, if you swap the first few outcomes of treatment and control, then this two-phase design gets totally screwed up, does worse than Bernoulli with p½ but Clip-OGD does not get screwed up in the same way. So it's my hope that this burn-in period can be made much less severe with like better types of algorithmic analysis. Okay, so we've shown adaptive allocations equivalent to online.
Really great.
Yeah.
So the difference between the two figures, like adversarial is the order thing on the right.
Just the first, yes, but just the first like sliver of the, yeah.
So it makes the wrong decision.
Yes, which is kind of like to be expected. It could happen. People could be going and not, yeah. Okay. Oh, yes. Okay, great. So we've gotten, we've shown that adaptive Neyman allocation is equivalent to an adversarial online convex optimization problem. We've shown this algorithm can achieve square root t, Neyman regret, implying that it will converge to the true variance. We developed tools for getting valid confidence intervals, and there's lots of future work. Like, is square root t the best? Can you get something that's like an instance optimal kind of rate? When can you get log t maybe? Central limit theorems would allow for tighter confidence intervals, and other kinds of problems. Well, if you have covariates, what can happen? Maybe you want to do some kind of selective inference. What can happen? So that's kind of what the future work is. I had a little bit planned about the other work that I do, but let me just say that it's on interference. Questions like, is there a protective spillover effect of vaccines on the unvaccinated, and everyone can interact in some kind of way, or can an increase in cash subsidy to some firm affect competing firms? So now there's interactions that were not previously there in the talk. So I work in kind of 3 areas. Can you estimate these effects well? And we have a lot of work on this. We've understood this kind of well. What we know less about is how to design the experiment when interference is present. You have to be taking the interference pattern, maybe the network, and what you want to estimate into account, which is kind of a challenging problem to get solid theoretical guarantees on. So I've been working on that. And finally, robust inference. What if your interference model is misspecified a little bit? Are your inferential procedures still valid? And can you test for those kind of misspecifications? There's many open questions, many exciting opportunities there. I'm happy to talk about that. Thank you so much for your time. I'll happy to answer any questions we have left. Thanks.
Yeah, I'm just curious, the omega T lower bound you have on the same thing. Is this like critically relying on the fact that like the units are not coming to IID? And it's like a fixed sequence, or if the units were coming to IID, there's no other way?
It also holds for IID. Do you mean like this contrast between cumulative regret and Neyman?
No, I mean you have this first. So there's like
Oh,
first thing on additional results where it's like if you have a 2-stick thing, it's omega T, but
yes, no, that is relying on the fact that I could mess up, like any stage you give me, I could mess it up. That's the idea. Yeah, you'd have to be, yes. People haven't done it up until, I think there's a paper I just heard about last week that has done that. But yeah, it's yeah. Nice. Any other questions here? Oh, last one. Yes. I don't know so much. There's lots of like Bayesian adaptive designs in like the 70s, 80s, and 90s, but I don't know as much. They're oftentimes they're trying to do things that are very different, like minimize posterior risk or something like that. I don't know of like specific allocation rules that target specifically like the variance of some estimator. I'm not as much of a Bayesian, so I don't think I gave a very good answer there. But I'm happy to point you to a survey that I put up here. Awesome. Nice. No, I don't have a very good answer. Awesome. Hey, thank you so much for having me here. This was great. Thanks.